Hello everyone, so today's example is going to be going over Euler's method. So we'll be doing two examples for Euler's method today, and what it basically consists of is if we have a curve of some sorts, we can break it down using Euler's method by creating a straight line from this point. So calculating the derivative at this point to give us the slope, making a line from this slope, and then recalculating the slope at a different point, making another line, recalculating the slope at a different point, making another line, recalculating the slope at a different point, and eventually getting something that looks more or less something like this, something that works like that. So that doesn't exactly roughly follows the structure of our curve, but doesn't exactly approximate it, but is a lot closer than just doing one whole linearization here. That doesn't get us very far. So it's basically the happy medium between taking a linearization and doing Taylor's approximation. So that being said, what we're going to do really quick is just go through two examples. So I'm just going to come up with this one on the fly, where you basically, what you're going to be given there, two possible ways these can be formatted. Either they do this first example, or either they do what I'm going to do the second example. So dy dx is equal to, I don't know, I'm going to do something like 3x plus y, right? And then what they'll do is they'll say, we start at x equals 0, and then at x equals 0, y equals 1, and then we're going to have a step size of 1. So step size of 1. Actually, we'll do 0.5. And let's say we want to find the approximation for y when x is equal to 1, right? So that's two steps because 0 plus 0.5 is 0.5, 0.5 plus 0.5 is 1, so it'd be two steps of step size equals 0.5. So what we're going to go ahead and do is this is going to be the equation that tells us the slope. So what we'll do is we'll have three things here. We'll have our x value, we'll have our y value, and then we'll have our derivative. Basically, I don't know, f prime of x, right? That's just the equation's derivative. All right, so our x at the beginning is 0, our y at the beginning is 1, and what we'll do is every one of these has the n value, and then we have our derivative, which we'll calculate here. Sorry, let's do that really quick. So 3 times 0 is 0, plus y, which is 1, is 1, so f of f prime is 1. And what we'll do here, actually, is every single one of these steps has the next y value derived from this equation that I'll show you right now. So let's fill out the x's real quick first. We know that it's going to increase by 0.5 each time because we have a step size of 0.5. And then what you'll see is that we have this equation. So the next value of y, which we'll call y sub 1, is equal to the existing y value, which is just y naught, the original y value, which is this, plus our step size, which is 0.5, times the derivative. So the derivative, we now know, is 1 at this point. So 0.5 times 1. So we know that our next y value is going to be 1 plus 0.5 times 1 is 1. Oh, sorry, 0.5. Now, the next value is 1.5. And now, we just do this again. Okay, so 3x plus y, our x value here is now 0.5, and our x value here, y value here is 1.5. So 0.5 times 3 is 1.5, plus 1.5 again, because it's y. So that means that we have 3. So our derivative here is 3. And then we just plug in again. Our next y value, y naught, is equal to, y prime is equal to y sub naught, which is this value, plus our step size, 0.5, times the derivative. So 0.5 times 3 is 1.5, plus the original value, 1.5 plus 1.5. Our value now is 3. And you might even see a pattern emerging here, because you notice that our next y value is just our step size multiplied by this, is that. So our step size multiplied by this is that, and that's because that's this equation. So eventually, once you get good enough to recognize the pattern in the table, as opposed to writing the whole thing out, you could just, repeat the pattern over and over and over again. All right, so that's one example that they give you. And there's another set of examples that's a bit more complicated that appears on Khan Academy a lot. So I'm going to take this one straight from Khan Academy. That way I don't have to come up with it on my own. And it says dy dx is equal to 3x minus y. And I'll read it out loud. So let y of equals g of x be the solution to a differential equation with the initial condition g of naught equals k. So basically, g of naught equals k. G of 0 equals k. That's what it says. Where g of 0 equals k. So that basically means our original x value is 0. g of 0, and then g of 0 is just y. So y equals some value k. So basically we don't know where we start from. But if we make our table, x, y, and then our derivative, we know that we start at 0, k, and then we can calculate this. Or we can't calculate this, actually. Oh, sorry, this is 2y, by the way. I probably said that, but there we go. Okay. So we don't know where we start, but we might be able to know where we finish, because it says where k is a constant, Euler's method, which starts at x equals 0 and a step size of 1, so our step size, which I'll call n, is equal to 1, gives the approximation g of 2 is 4.5. So we know that we take a step size of 1, and then we get to 2, and then it says g of 2 is 4.5. So that means that this is 4.5. So find the value of k. So at this point you might be really confused. You might have no idea what we're supposed to do. And that would honestly make sense. This is very confusing. But what we can do here is sort of calculate where we're going to go from here. We can kind of see where this will eventually end up. So first of all, we know that 3x minus 2y is equal to 4.5, specifically for these values. So let's ignore the beginning first. So we know that for these original values, I'm going to create values. I'll just call this is x, this is our value y, and then this is our derivative, right? And our derivative is this equation, 3x, or 3 times 1, 3 minus 2, this value y. And then we don't care about the derivative here. We're just trying to get this value. So we know that for a fact that y, this value y, plus our step size, which is just 1, times 3 minus 2y is equal to 4.5. So we can solve for this value of y fairly easily, because we can just solve, okay, y minus 2y is just going to be negative y. So we know 3 minus y is equal to 4.5. So what we're going to do is just do some quick maths. 3 minus what number is 4.5? Well, 3 minus negative 1.5 is 4.5. It's just solving the equation. So we know that the y value here is negative 1.5. Cool. And then this is just whatever f prime is. Okay, and now we just do the exact same thing again, except 3 of 0, we know that this value k, cool, plus 1, because that's our step size, multiplied by 3x minus 2y. Well, what's our x value here? Our value here is 0, so 3 times 0 minus 2y, in this case y is k, so basically it is equal to our new value. Our new value is negative 1.5. So we know that negative 1.5 is equal to k plus negative 2k, because y is equal to k here. So k minus 2k is equal to negative 1.5. Okay, if we simplify that, k minus 2k is negative k. Negative k equals negative 1.5, so that means if we take the negatives away, k is equal to 1.5. So that's our existing value. And we now know that this y value is k, but it's also equal to 1.5. So that gives us our answer. So those are the two types of problems that you'll see with this wording. Hopefully that helps you, and I hope that everyone has a nice rest of their day or evening.